So this is going to be the agenda for the session. So first I'll be laying the groundwork. So I'll be trying to talk about what's the current scenarios and what are the challenges, etc. Then I'll be talking about some of the application design guidelines. So these are more like a little bit of design patterns kind of thing, like what are some of the key concepts that you have to think from an application design perspective. Then we'll talk about what are the different cloud native models which are there as of now. We'll talk a little bit about infrastructure design guidelines from a cloud native perspective. So we won't be going into the immutable lifecycle, etc. So my colleague Terence will be talking about AMI lifecycle by using HashiCorp and AWS tools. And finally, we'll be looking at some of the examples, cloud native in action, where if you do cloud native truly, like what will be the benefit that you'll be gaining from it. So first is, what is cloud native? So this is a definition that I picked from CNCF. So CNCF is Cloud Native Compute Foundation. So which is like an organization which is trying to lay out, how many of you are familiar with CNCF? A lot of you. So yeah, so CNCF is primarily like this organization which is trying to consolidate all the cloud native technologies, bring it under a single umbrella. So a really good thing that you can check out is CNCF landscape. So if you just go to CNCF landscape and then you can pick out each of the different tools which are there. So this is how CNCF defines it. So cloud native technologies empower organizations to build and run scalable applications in modern dynamic environments. Now the key parts here is empowering, scalable and dynamic, right? The main part I wanted to focus is when we say cloud native, it is not necessary that it has to be for a specific cloud, or it's a methodology of doing design and development. So the key part is in cloud native, you can't predict where your workload is going to be running. So that is the first mentality that you need to be aware of. So it could be anywhere. So it could be dynamic. So you can't predict it upfront where it's going to be running, which means that there are some challenges and there are some concepts that you have to be aware of, which I'll be talking about. And of course, it helps in terms of scaling. And it's an umbrella set of technologies which work together. So that's what cloud native is. Now, what are the challenges? So I think the principal challenge for cloud native is that there's a lot of ambiguity in what cloud native means. And I don't think everybody has a consistent definition of what cloud native means, which is fine because it's difficult to define it. But cloud native is something which has evolved organically over a period of time, over last 3, 4, 5 years, right? It's something which has been evolving organically. So which means that everybody's definition of cloud native is different. And I think that's a key challenge because when I say like I'm doing cloud native and somebody else says they're doing cloud native, third person says something, we three might be talking different things, right? There might be some common elements like Kubernetes or something of that sort, but that's probably the similarities which will be there. So that's the key thing which is there, which is we need to have a clear understanding of what exactly cloud native means. The second part is from an architecture and development standpoint, there has to be a significant shift in terms of mindset. This is something, I think there is a lot of movement in this, but I think there's a lot more to be achieved in terms of this mindset shift which is required. The third point is fear to experiment, evaluate, and switch between languages and framework. This is something I've seen a lot because a lot of organizations would have these things, and I don't mean it as disrespect for anyone. A thing like, okay, we have like a lot of Java people, so we'll stick to only Java, right? Or we have only Python, we'll stick to only Python, etc. But there must be a certain willingness to switch between things, experiment things, but at the same time, it has to be practical as well. You can't just keep switching whatever is coolest, like every 6 months or something. That's not practical either. But there must be, we must overcome this fear because there are pros and cons for each of those things. The next point is about determining microservice boundaries with loose coupling. I'm sure a lot of people who have worked with microservices will have this experience. So you build microservices, you think everything is amazing, all is good, you deploy things and all that stuff. Now the problem that happens is one of your microservices goes down, it brings down the entire system. Now, is that what really the ethos of microservice is? Because you should be truly able to operate independently. And so what happens is, it's difficult to draw the boundaries of microservice. You think that this is a microservice and you go ahead and make it a microservice. But once you are, and that's what boundaries mean, service boundaries. So boundaries is a concept that you will find with topics like domain-driven design and CQRS, etc. So if you're not able to figure out the boundaries correctly, and if you lay down wrong boundaries, you're going to be in a lot of, you'll be in hell basically afterwards, right? Once it goes to production, etc. Because you'll have to then go back and change everything. So The fact here is that with microservices, you need to have loose coupling. So if you create microservices with tight coupling, might as well have left it as a monolith. There's no other point that you've done. And finally, the increased complexity, right? Because when you have like tens of hundreds of microservices, how do you handle complexity, right? How do you handle deployments? How do you handle things like, the service has to come up first, the dependencies between the services, etc. So these are some of the challenges which are there. So yeah, how you will benefit from this session. So I just tried to list down like, audiences must be diverse here. So there should be business owners, architects, both solution and tech, delivery managers, developers, and ops. So from a business owner perspective, the key thing is, of course, rolling out features faster, which is straightforward, but significant cloud cost savings will be there. From a solution architect perspective, now this is really critical. This is something which I see is overlooked quite a lot. Solution architect is supposed to be the glue, the connection between product and the execution, right? So you'd have to work, the solution architects would have to work with the product teams, with the UX teams. Now, when the solution architects craft solutions to business problems, it is vital that you do it in the context of cloud native. You need to understand what are some of the opportunities as well as challenges which is there with cloud native and develop it accordingly, because you will see a lot of cases where you'll develop solutions which are very synchronous, which doesn't work in an asynchronous model, right? And then you will have a nightmare because the development teams will be trying to do it, but they can't do it, and then they'll run into all sorts of problems. So as a solution architect, it's vital that you understand what is cloud native and how is it different from the previous architectures, and what are the opportunities and the changes required. From a tech arc perspective, you need to understand about what are the models which are there which can be used to develop your application, design it accordingly so that you can deploy it within the various cloud native models which are there, as well as picking toolings for development, deployment, and maintenance, because there's a lot of tooling required in cloud native because you have a lot of diverse set of technologies and a lot of different microservices. From a delivery perspective, the challenge again, which I've noticed a lot, is adapting to the cloud native lifecycle, right? Because you're used to a certain SDLC and you don't adapt to the cloud native lifecycle. That's really important. And that will also help significantly in terms of reducing the technical debt. Because one of the things, if you saw back to the definition of cloud native, was that it would run in any sort of environment, right? You can't predict it upfront where it's going to run, which means that you, as a developer, you're forced to think in terms of things like scaling, exception handling, failures, all those things. You're forced to think about it upfront. So those kind of things will help in terms of reducing the technical debt, because you're not just focused on cranking out features, but you're also focused on addressing some of the non-functional parts as well. So that should help in terms of technical debt. From a developer perspective, understanding the development and testing methodologies, especially with respect to TDD, some asynchronous programming, etc., as well as the DevOps culture, which is straightforward. From an ops perspective, it's about maintaining higher uptimes of your application and SLAs without getting burnt out. Because imagine if you have hundreds of microservices and they're all tightly coupled together, you will get burnt out. Because one of the microservice fails, it'll bring down significant parts of the system. As well as fastening your response cycle to the issues which are there, which you'll have to close. You'll have to have enough of observability and instrumentation so that you can collect the data, analyze the data between the developers and yourself, and then you can come up with the solutions for that. All right, so moving on to application design guidelines. So why did I pick up application first? Because this is a conscious decision that I've put application first, because when we talk cloud native, there's a, I don't know if it's a misconception or not, but there's a feeling that I get that always people jump immediately, oh, let's do Kubernetes, right? Cloud native. Let's go to infrastructure, dev, it's not my problem, right? It's the Kubernetes guy who's supposed to make it cloud native. It's not. It starts all the way from application design onwards. So the first point is that from an application design perspective, from an architecture perspective, as well as design and development, it is vital that we embrace distributed systems and patterns. It is so vital that we do this because your applications will be running in distributed mode, which means that when you develop your application, as well as when you use technologies to work with your application, like whether it's Zookeeper or whatever it is, you need to understand what distributed systems are, what are some of the opportunities there, what are some of the challenges there. So starting in distributed systems, a good starting point would be what is called as a CAP theorem. How many of you have heard of CAP theorem? Yeah, so CAP theorem is basically like this thing where you can have like, so you have got consistency, availability, and partition tolerance. So that's what CAP stands for. So you can have only two out of these three. That's a basic catch. You can't have all three, right? So now, if you can only pick, and there are catches here. So for instance, if you take consistency and availability, you have a possibility that the data might be unavailable. If you pick up availability and partition tolerance, you might have inconsistent data, which is like eventual consistency. Like Cassandra is a classic example of that. If you pick up CP, you'll have another part. So you will have to make this choice, and you will have to understand that you can have only two out of these three things. That means you will have to let go of one thing. Now, that's going to be the part where when you do the design, when you pick up the components, you have to decide that of these three things, what do you want to let go of? So that's a good starting place for distributed systems. The other part is there are some architectures which are there in distributed systems. Again, you can read up about this in more detail. So typically you will have a master-slave architecture or a P2P architecture, right? So in master-slave architecture, you will have a primary, and you will have a bunch of worker nodes, slaves, nodes, whatever you call it. In peer-to-peer, you don't have any masters. It's just all of them talking to each other. Gossip protocols are there, which are used for communicating between each other. Typically, that will be eventually consistent because you will not have the data available in all the nodes all the time. Whereas in master-slave, you will have more of consistency with data. There are a few other concepts that you need to be aware of. The terms like heartbeat, leader election, and quorum. So quorum is something where when you do a master-slave architecture, you need to have like typically an odd number. It is just meant for resiliency purposes. And how it understands whether the nodes are alive or not, because these things are distributed. They're spread over, like software networks or even actual network, but typically it will be mostly over a software-defined network, like an overlay network. So they will communicate by using heartbeats. And if it doesn't get a particular heartbeat within a certain period of time, master will assume that it's dead, which means that you can start spinning it up and all that. Peer-to-peer is different because there is no master there. That's a key point. So all the nodes talk to each other. It's like a ring structure. Shared nothing. Now, shared nothing is not related to these two per se, but shared nothing means that so typically you will have always CPU, memory, and storage, right, to execute anything. And of course, you've got the network, which is there at the top. So shared nothing principle is that you should not share any of these resources between the different nodes or the different execution units which are there. Now, the reason why it is important to not share is, one is if you share, there's a possibility that one of the nodes might corrupt the other node, right? So you might have situations where one will take down the other. But more than that, the key part is whenever you want to scale up or down, you have complete freedom now because you don't have any sort of shared parts. Everything is separate. You can spin it up, spin it out, spin down, whatever it is. So you have got complete control over there. Of course, there's more complexity which comes in. So these are some of the architectures which are there in that. Right. So this is one of the key parts that I want to talk about because I'm not sure this is well understood and this methodology is well understood because I've seen this go wrong so many times over so many years now. So a lot of you might have heard, whenever you start design development, you should do microservices. You should avoid monolith at all cost, right? Monolith is a term which is almost gone people really hate monoliths right now. But my take, and I think a lot of people talk about this as well, is that you should not see monolith as something which is bad. You should be okay with monolith. And the reason why I'm saying that is, it's always better to start off as a monolith. Okay, so let's assume that you're starting, you have no idea you just got a bunch of requirements, etc. So you have to start designing and developing and all that. At this point, if you start thinking that, hey, like the typical classic example that they give, products, orders, shipping, etc. Those examples look really simple. They're meant to give you an idea of but in your requirements is not going to be so simple, right? So you will start thinking okay, let me start trying to copy what somebody did, with products and orders and all that. You'll go ahead and you'll start splitting this up and all looks great. But finally, I'm telling you, it'll be like a tightly coupled spaghetti which is going to come out, right? So instead of that, my suggestion would be start off as a monolith. There's no shame in talking monolith. There's no shame at all, right? Start off as a monolith, then sit back, relax, do your development, continue for a while. At this point, you will start seeing some of the boundaries emerging in your application, right? And a good example of that, not related to this, is that So let's assume that we have this room, right? We have this hall here, right? Imagine like you put 100 people inside, okay? Now 100 people eventually, they will start forming their groups, right? People who have like interests or whatever, they'll start huddling together, they'll start forming a groups, right? At this point, I can say, okay, that's one set of group, that's one set of group. Now imagine doing that versus me deciding upfront that, okay, 5 of you, you should sit together. 5 of you, you should sit together. 10 of you should sit together. I think that you have like interests, but the people probably don't have the like interests. It's the same thing that happens. If we start enforcing microservices upfront, you do not know the domain well enough. You don't know the requirements well enough. You're still working with the SMEs on that. So start off as a monolith, sit back for a while you're doing development, you will start seeing that the boundaries will start evolving over a period of time, sort of like an evolutionary architecture. But the catch here is that when that happens, you need to be 100% sure that you have a TDD approach in place, right? So I'm saying that don't shun monoliths at the beginning, go with monolith, but make sure that you have a TDD approach. Because now when the boundaries are evolving, you need to start continuous refactoring because you need to start adjusting. You will start seeing that, okay, I need to put this within this boundary, that within that boundary, etc. You'll start seeing this. But when you do this, how are you going to refactor it if you don't have TDD, right? You'll have to do it and you'll have to spend a lot of time. You'll not have the confidence that, things are working fine, etc. So that's why I would say monolith with TDD, start there. Let it evolve, do continuous refactoring afterwards. Now there will come a point, depending on the life cycle of the project, how long the project is, how complex it is, typically in the order of 6 months or so, where you'll get a call and say like, okay, what's the deployment architecture, right? So you'll have to say, okay, what's the production system going to look like? Now this is the point where you can start thinking about how do you want to, of course, how do you want to deploy it, but you can start thinking about, okay, what parts have to scale independently, right? What parts have to be fault tolerant? You can start thinking about it. Now, once you have a clarity, only at that point, break it into microservices. And that too, let's assume that you start with your monolith and it has 5 boundaries at this point. But when you go for deployment, you may realize that you want only 2 of them. Break out only those 2. You don't have to break out the entire 5. So break it only when absolutely required. And then you can test out the coupling, whether you do manual chaos engineering or by automation, where you can try taking down a few of the services and see like, how does it hold? Now you will be in a situation where you will have loosely coupled microservices and repeat this process over. So this is a very important concept that I wanted to convey, and it's called as service boundaries. So if you go and look into domain-driven design or CQRS, you will see service boundaries a lot. So understanding service boundaries and breaking it up such that there's loose coupling is a very vital point, because otherwise Kubernetes or even God can't save you. So that's very important. The next part is deciding the languages and frameworks. So this goes back to the point where I was telling about fear of deciding between what different languages and different frameworks, etc. So a lot of people talk about how do you design. So some say like, I like this particular language because it looks cool, or this looks clean, or I have the resources, etc. Which is all fine, which are secondary points. But the key part is, the key question that you need to ask yourself is, the workload which is there, what kind of a workload is it? Is it a CPU intensive workload or an IO intensive workload? There are differences which will come up based on the options which will be, you'll be suggesting. If it's based on this, it'll make more sense. Like for instance, event loop, as you know, there's Node.js and all those things. For multi-threading, you have like Java, etc. It's not that you can't do multi-threading with Node, you can still do it. You'll have to change a few things. Neither is it that you can't do event loop with Java, you can use frameworks like Quasar, etc. But understanding this question, that when you look at languages and frameworks, first think, what is a workload like? Is it a CPU intensive workload, which means that there's a lot of transformation, crunching, etc. Or it's an IO intensive workload where there's a lot of network calls, etc. Understand that, and based on that, you can get your language and framework options. The next part is, this is more like a observation. Typically, when we talk about design, we always tend to talk about the design patterns, especially architects. And they tend to talk about Gang of Four or those kind of design patterns, solid principles and all that. Now, one thing to remember is that those things are great. I'm not saying that those things are not great, but remember that those things come from an object-oriented background, one. Second is, they come from a time when cloud native wasn't there. They come from a time when monoliths were there, like significant massive monoliths were there. So it's not that those things are bad, but I think there's a need also to embrace new things which is happening, and that's primarily functional programming, right? The key takeaway here is that functional programming, you can check out any language like Scala or Haskell or anything. Try out any of these languages and just get a feel for functions, partial functions, currying, etc. But the key thing is, the two things I would like to highlight is stateless and immutability, right? So stateless is something which says that if you have a function, and so like f of x is x into 2, you just pass in a number, it'll just multiply by 2 and give it to you out, right? This is a very powerful concept because that can directly be used for doing really simple transformation like succinct transformation, but most important, you can do multi-threading really amazingly well with functional programming languages. It's not that you can't do multi-threading with Java, etc., but the chances are if you don't design it well, you will have a shared state. If you have a shared state, you will have to put a lock. If you put a lock, you will have blocking. So when you talk about stateless, immutable functions, you don't need locks anymore. That is the key part where it helps in terms of performance. And then you'll have to, of course, look at existing ecosystem and trends. So there are people who like, oh, 1 month back a new language has come out, looks cool, I'm going to do it, I'm going to write everything. That's not practical either. But at the other side, it shouldn't be like we will do only this particular thing, because there are opportunities to design your microservices. Like you can have probably Python, Java, Scala, all a mix of things, but it has to be evaluated based on these criteria. The next point is about synchronous and asynchronous processes. So on the left hand side you have a synchronous, and right hand side you have asynchronous process. Synchronous means that it's like one guy is asking, there's a request response cycle. Asynchronous means that you're publishing an event, somebody listens to it, right? Often we hear that people say like events are cool, right? Event driven architecture, really cool. So let's go with events for everything. So you go with events for everything and all that stuff. Suddenly one fine day you realize that, oh, I need an RPC style thing. I can't do events, like I can't fire and forget, I need to get information back. What do you do at this point? You're left with two options. One is you create RPC on top of asynchronous process, right? You create a pseudo synchronous kind of thing, right? Like a fake synchronous kind of thing, which will affect in terms of performance. Or you could have been smart and you could have embraced both parts, right? You don't have to be biased only towards event-driven architecture. You can still have RPC also. Good examples of this, or the latest, the currently trending framework is obviously gRPC from Google, Protobuf's serialization. Or you can even use straightforward REST APIs. It'll be not as efficient as gRPC, of course. So there is no particular necessity that microservice to microservice communication should be only via events. Yes, it introduces loose coupling and all that, but it's not a mandatory thing. You can still have synchronous communication, and if you're worried about coupling, you can use like service discovery and locator patterns, etc. So that's about synchronous and asynchronous. When we do events, it is really important that you pick up a schema library like Protobuf is a good example, because one of the things that will happen is as your microservices evolve, microservice 1 will be worked on by team 1, microservices 2 will be worked on by team 2. They agree on everything. Say like microservice 1 is publishing something, 2 has subscribed to it, everything looks fine. Till one day, team 1 changes the schema definition of the event, boom, gone, right? Microservice 2 breaks completely. So to prevent that, you need to enforce the schema, and Protobuf is a good way of doing it, or any ideal based support which is there is good to do it. But apart from this, it will also help you to reduce your bandwidth significantly, because it's binary compression which is happening there. So never use JSON directly for sending events across microservice. Always go for Protobuf or something of that sort, so that you can enforce the schema. Alright, so this is the next part. So this is going to be a section about, so we briefly spoke about stateless with functional programming. We'll take it a next step forward. Instead of just functions, we'll talk about stateless and stateful components itself in the system. So this is the classic analogy which is there in the DevOps space. So you've got pets and cattle. So you treat your pets and cattle differently, right? So you've got pets who have got a particular name, you bring it up, they're close to you, etc. I'm not saying cows are not close to you, can be close, but you have like a distinction between how you treat your pets as well as how you treat a herd, right? So if a pet disappears or a pet is gone, You'll have to bring up a new pet, you'll have to put a name to it, you'll have to take it through the whole life cycle, you know, learn how to live in your house, etc., and all that, all those things, right? Whereas if a cattle is gone, or you need more cattle, you can add it instantly, and that's why you have those, like, random kind of numbers, name is not specific, etc. Now, why is this important? Now, if you adopt this mentality, always what we work on typically is that we work with pets, right? We have a application which talks to the database, a specific database with a specific connection, with a specific set of schema. Like, we are so caught, and we have all these kind of applications. Now, if this application dies in production, right, it goes down, you will have to do so many cleanup steps. You'll have to make sure that so much, whatever initial steps which are there has to be created, like all sorts of dependencies will come in, right? And that hampers how you can, because remember, again, cloud native means that you can't predict where it's going to run. It's going to be dynamic, right? So you will be in a whole lot of pain if those applications go down. You'll have to make sure that they are cleaned. The new thing comes up, it starts. You need to ensure that, logs, etc. All these kind of complications come up. Whereas if you have components which don't maintain any state, right? Just like functions, but think in larger term, components, they don't maintain any state. They read something, they pass something to them, they process something, they spit out something, right? That means you can now scale it. If they die, you can replace it. You don't care. Probably you just have to keep a number like, okay, I need 5 of these guys to be around. I don't care what the identity of them are. So that's what this analogy is about. So the takeaway here is that when you are having your components, try as much as possible to have stateless components, as much as possible. It is not possible in all the cases. Some cases, of course, you'll have databases, you'll have message queues, etc., which have an inherent state. But as much as possible, try to use stateless services, which means you can scale it, take it out. It's all very easy to automate it, and from a complexity perspective and management. Now, if you are left with no choice but to have state, isolate those ones out, specifically only those. So let's say you have like 50 microservices. If you can have 40 of your microservices to be stateless, great. You're left with only 10 of those microservices whose state you have to handle. Now, when you have to handle, remember, do a shared nothing model. Now, once you come to the shared nothing model, you'll have to pick up a DB. Make sure that you pick up a DB based on the pros and cons of each of the databases which are there. Don't directly jump between, say, like SQL or Mongo, right? Investigate a little bit more, because there are search databases, key value, columnar databases. Each of them have their pros and cons. So investigate that, and based on that, pick up your database, but try to keep it minimal. Now, this is another approach. In case you don't want to keep a database kind of thing, which is a little bit complicated to manage, that's one. The second part is when you make database transactions, typically there is no audit maintained for that. So if you have to go back in time and find out, okay, my data got corrupted, what was the time at which it got corrupted? Was it 5 days ago, 10 days? I have no idea, right? I need to figure out when it got corrupted. That is difficult in database if you just use databases, because you will not be keeping a record of the transactions. So in such cases, as well as to simplify it within a message queue kind of a structure, there is an architectural pattern called as event sourcing. So event sourcing is something where you treat any state change in the system as an event. So something happens, it's an event. Any state transition is an event, and all you do is you keep a record of the events. That's all you do, in the order that the events were, right? Now, the beauty is that if you have this particular system, let's say the application crashes, you just play back the events in the same order. The application will be back up. So it is like stateless systems where you have kept out the events in a separate store. You just have to play it in the order. You can pause it, rewind it, go back, forward, etc. You automatically get audit functionality as well. But does that mean that you have to do event sourcing for everything? No. This is something that you have to make a call. Do you require, do you have auditory requirements, etc.? Then definitely you should consider event sourcing. Now, this is something which is, so you have a producer, you have a consumer. Producer is producing some events. Application is transforming those events, again, sending it to some events. And then consumer is consuming. Straightforward, right? It's exactly like event sourcing. But the problem is, and this is a very key point, event sourcing is always done in the microservices world, right? It's done by cloud native people, etc. Stream processing is always spoken about in the big data world. Now, what is happening is, if you look at frameworks like Kafka streams, Akka streams, etc., there is a new paradigm which is coming in, which is mixing of both big data and microservices together, and those are called as streaming microservices, right? So, streaming microservices is something definitely that you have to watch out for. It is a mix of both the worlds together. So here you have a unlimited amount of streams or something which is coming in. This could be Kafka or whatever it is. Application probably has an embedded Kafka streams inside it which is processing it, maintaining a state in some sort of a database, and then passing the results back, which then other consumers are consuming out of it. Now, if you go back, that's exactly what event sourcing is. So there is a mix coming up where the microservices and big data world is colliding. So this is something that you have to watch out for, because if you wanted to do stream processing today, everybody will say, oh, go for Spark or Flink, right? That's what stream processing is. But it is not necessary. Start thinking about stream processing also in the context of your applications as well, microservices. So read up about reactive streams, Kafka streams, etc. Those are movements which are happening into that space. The next part is about handling failures. So here the key thing is, consider that your whatever calls that you will be making will fail, because again your environment is dynamic. Things may not be up when you make a call. So handle those things. Some of the options are timeout and retries. Those are straightforward. Circuit breaker is a pattern that you can read up, and dead letter queues are typically something which is used to hold unprocessed messages so you can play it back again. From an instrumentation and observability, very vital, again, because it's dynamic environments, you have no control over where it is running. Logging, monitoring, and tracing, especially distributed tracing, right? Because you want to trace it across your microservices. So this is something which is really important to consider as well. Now I'll briefly go through 3 of the different cloud native models which are there. So microservices, we already spoke about microservices. You can have your shared nothing databases, etc. You will have your message queues. Typically, you will have like an API gateway, which is the interaction to the microservices, and that's where API gateway to microservice communication is a synchronous thing, so you'll have to consider some RPC framework. You will manage this and deploy this in a Kubernetes cluster, etc. So that's straightforward. Serverless, I'm sure there'll be a lot of talks today about serverless, right? So that's fine. So I'm not going to cover serverless much. This is another model which is there. One model that I do want to talk about, which is not talked about much, is have you guys heard about Reactive Manifesto? How many of you have heard of Reactive Manifesto? Oh, that's good, promising. So there is a thing called as Reactive Manifesto. Have a read about it and look at reactive programming. So you will see like it's coming up in a lot of frameworks like Java, etc. And it's a way of, and even on the client side as well, because you have got observables in Angular, right? So it's the same thing. So reactive programming is a style of programming where you can consider the same thing just like what was there here. So it's reactive programming. You have an unbounded event of streams. You are doing transformations real time on top of that. So that is reactive programming. There are a lot of frameworks for that now. Another model that I want to talk about is what is called as an actor model. So actor model is something which comes from Erlang, and the implementation of that in JVM is Akka. So just have a read about actor model. This is not something which is any different from microservices. It's a more of an opinionated way of doing microservices, but it is really good in terms of handling exceptions, clustering, scaling your applications, etc. But bear in mind that this is a little bit steep from a learning perspective, and it is not meant for every use case. It has to be used only where the scale or the requirement is so high. There's also an interesting paper from PayPal about how they have used Akka to reduce from like 10,000 VMs to 8 VMs or something. Reactive streams is another model. It's just like stream processing which is there, but there is a back pressure concept. This is meant so that publisher doesn't overrun. It's the same like publisher subscriber, except there's a control mechanism. So have a look at reactive streams as well. Again, this is going to collide into microservices world. So when you're looking at streaming microservices, reactive streams is going to come in. Now, infrastructure design guidelines. So from a compute network and storage perspective. So from a compute perspective, always target immutable infrastructure. So what is immutable infrastructure? You don't make changes on the infrastructure. You always make changes via code, you deploy it. So you don't touch anything. Maximize your stateless components, because once you have stateless components, you can offload it to spots. And once you go to spots, you get crazy savings. Use RIs and savings plans, which is there now for stateful components. For storage, EBS is straightforward. Consider RAID and LVM because this is something which can increase your performance. file systems is something to investigate. I would also like to point out the last point, which is try to use S3 also as a general file system, not just as an object storage. You can use layers on top of it. A good technology is Aluxio. It is a layer on top of it where you can create like fuse mount systems on top of that. So definitely S3 is something which has to be looked at. From a network perspective, serialization, chattiness, but one thing I would just like to highlight is placement groups and rack awareness. Because what happens is when you have inter-region or cross-region communication, you will be charged for it. So as much as possible, you should, because you have distributed systems, they're all sending heartbeats to each other, etc., all that stuff. Try to put it within a same region, and that's where you can use placement groups and rack awareness for this. A lot of the frameworks support rack awareness, a lot of the databases, etc. You just have to make sure that it falls within the placement group, you put a label, etc., and manage the life cycle of that. So that's from the infrastructure optimization. I'm not going to specifically talk about CI/CD because everybody should be aware of it, but I would like to highlight DevSecOps or SecDevOps. It doesn't make any difference whether you call it Dev or Sec first. There's no difference. But what I would like to highlight here is that from a security perspective, there's a concept that you will hear, shift left, take security closer rather than, so the traditional model is you deploy it, go to some testing, and then you do pen testing, etc. So it becomes very complex to change it afterwards. So try to bring it into the dev cycle where you can have things like static code analysis, package vulnerability, container scanning, etc. right in your CI/CD pipeline, and that's DevSecOps. Observability, so this is a straightforward thing. So you're taking from CloudWatch, you're sending it, looking at particular conditions, and then you're sending it out to different places, as well as you're maintaining a set of all the logs in Elasticsearch. It doesn't specifically have to be Elasticsearch, but the point here is that if I want to go back in time and look at logs, I should have it. If I want to get notifications if something has happened, like monitoring perspective, like spikes on CPU, network, etc., which is not expected, I should know about it. So that's observability. Event remediation is basically once I detect something, how can I remediate it automatically? So this is also something which is, you can just, same thing, you can just look for certain events which have happened, and then by using something like Lambda or your own thing, you can apply the condition. So this particular case is about security, so you can close based on suspected network connections. You can apply the logic, you can apply the blocking in your NACL or WAF for blocking those connections. So this is automated event remediation. Now, without a human being involved, you can do it. Finally, I want to talk a little bit about two of the cases. This is just to show you what is the potential that Cloud Native has if it's done properly. So this is a case about processing about 10 plus billion events per day, right? So we had a large system which was struggling with scalability, latency, and all those things. So we changed that entire thing, and it was all about processing these many amounts of events per day, and we moved it into reactive streams, used stateless components, and deployed over spots, orchestrated by using Kubernetes. Lambda architecture is something in big data because we wanted to leverage S3 for a lot of data saving, and that's the results that we attained. So 40% reduction in cost, right? And we're talking about tens of thousands of dollars here. So 40% is a huge amount, right? While doing that, we have got a 10x times reduction in terms of processing latency. We have got 5x times more. We could initially start with only about 2 or 3 billion events. Now we are at 10 billion events, right? And our query performance. So this is specifically because we have to analyze that data. It grows as well. So if you do Cloud Native all the way from scratch and not just at the end, there's a significant amount of cost savings, performance, both parts coming together. This is another use case. Primarily, this is about migration of a data center, like a large data center. We used SMS from AWS, blockchain-based. We optimized all the system, all the services to be cloud native, and again orchestrated by using Kubernetes, instrumented, optimized. And again, we have got a 30% reduction and 20x in terms of deployment velocity, but that's because pipelines were not there earlier. But the part that I want you to focus on is about the cost. So once you do it right, that's what you will end up with, right? You will get really great performance, like X number of times performance, and a significant amount of cost savings as well, courtesy of spots, plus using S3, etc. So you'll have to find that. So yeah, so to summarize, we spoke about the different models which are there, distributed systems, embrace distributed systems, really understand distributed systems, always think stateless versus stateful, and try as much as possible to use stateless. spoke about DevSecOps, observability, cost optimization. If there's anything that you would like to discuss with me or with us afterwards, like there's a booth, so you can just come out there, catch me anytime, discuss anything. So yeah, that's it. Thank you.